All right, so we are going to start Unit 8, Part 2. We're going to look at two things in the next series of videos. They're going to be small little bits and pieces. This can be really confusing. You're going to have to spend a lot of time kind of dissecting and understanding what titrations are, which are basically the physical kind of process of monitoring acid-base chemistry, and understanding how to represent those stoichiometrically, using rice tables, and graphically. So I'm going to break these videos up into some very small pieces. Now, I'm also going to change things around a little bit from what I did last year, and that we're going to tackle titrations first. I'm going to follow the College Board process in this case. And I'm going to start with titrations, introduce a little bit about buffers, and then we'll do buffers at the end of the week, which they're just a little bit more complex kinds of acid-base chemistry. Now, back in Chapter 4, when we looked at different kinds of chemical reactions, we looked at redox, we looked at precipitation reactions, and then the third category were acid-base. And we kind of left that to the side. Basically, that general category involves, there we go, an acid plus a base to make a salt and water. And that's kind of the basic chemistry. And so if I take something simple like hydrochloric acid, sodium hydroxide, and I repair them, I get a salt and water. And so what we want to do first is talk about what the terminology is, what the equipment looks like, and all of that. You're going to do a simulation that's also going to show you that as well. So basically what happens is, with a titration, I'm going to get a known solution of a base. Usually the known solution is in what's called a burette. And so for those of you who did not have any experimental chemistry last year, may not know what it looks like, but it's basically a long, almost like a graduated cylinder, only it empties from the bottom. And you can measure how many milliliters of a solution you deliver from the bottom by looking at where you start, where you end, and getting that volume and saying, okay, I delivered that much liquid through the burette into some kind of apparatus where you have a unknown solution. Now, you can also reverse these. You can also have the unknown in the burette and the known in the flask. It really doesn't matter. But one is known, one is not, and you use the known to understand what the molarity or pH or concentration is of the unknown. It's incredibly important. It's used all the time in real life to determine the acid or base concentration of an unknown material. So we're going to go to 17.3 in the Faribault packet, and we're going to talk about kind of what we're doing here. So we're going to take an acid in the burette, or the base in the burette, whichever. We're going to add it to an acid or a base in the flask, and they're going to react with each other, and they're going to come together. And when the stoichiometrically equivalent quantities of each have gone all the way to give just a salt and water, this is called the equivalence point. Equivalence point. And it can be found using an indicator, because a lot of these solutions are colorless. And so what you do is there are a lot of dyes and different chemicals whose color can change based on the pH of its environment. So I can determine when I have reached this equivalence point by using an indicator. If I use a pH probe and monitor the whole process and follow either hydroxide or hydrogen ion concentration through the whole thing, I get a titration curve. And so this curve will help me understand what's happening. Now you're going to hear a lot of terminology. The solution in the burette usually is known, although in the simulation you're going to do it as not. It's called the titrant. And then whatever's in the flask is called the analyte. And when you have reached the end point, which is where the color change occurs, the titration stops because you've gone all the way to the end of the reaction. That's called the end point. And in that case, you can find what's called the equivalence point, and we'll talk more about what that means. later. Okay, so what we're going to do first is we're going to spend time on what we would call strong acid, strong base titrations. Now again, HCl plus sodium hydroxide reacting together to form a salt and water, that is a strong acid, strong base titration, and so I'm going to put these together. Now, basically, it's a lot like what we did with our precipitation reactions. We had a certain volume of a molarity of one, combined it with a certain volume and a molarity of the other, and calculated how much product we got. And that's exactly what we're going to go do here. Now, in this case, I've got a burette with 0.1 molar sodium hydroxide. The flask contains 50 milliliters of a 0.1 molar HCl solution. And so what is the initial pH of my flask? So what is the pH in this container? So basically what I've got is I've got the HCl here and the sodium hydroxide here, and I'm going to mix the two together. All right. So if I want to find the initial pH, right, remember that, and a lot of people forgot about this, that the pH of my sodium hydroxide, of my HCl, is basically the same. I can take the negative log of the concentration of HCl because all of my HCl is going to dissociate. So basically, the initial pH of this HCl solution is a negative log 0.10, which is 1. Now, what I'm going to do is I'm going to add some 49 milliliters of 0.1 molar sodium hydroxide to the flask. So now they're mixed together. And so my initial moles of so what I've got to do now is it's not going to help me to do molarity here. What I want to do is just stoic. I've basically added 49 milliliters of a 0.10 molar sodium hydroxide to 50 milliliters of a 0.1 molar solution of HCl. And let's see where we sit there. So the initial moles of HCl that I have, I just calculate like I always do, 50 milliliters. 1,000 milliliters is 0.1 molar, so that is equal to 0.005. I can do the same for sodium hydroxide, and I get 0.0049. Let me put it here, moles. Remember, I'm calculating moles. Okay. Basically, you do the same thing. You take this. I've got 49.0 milliliters times 0.10 moles of 1,000 milliliters, and that's how many moles I have. So that tells me I've got 0.0049 moles of this and 0.005 moles of this. So when they react, for every mole of these, I'm going to react with 0.049 moles of this to give salt and water. So how much HCl is going to be left over is just going to be 0.050 minus 0.049, or 0.0001 moles of this is left over. So what that means is that if I have how many liters of solution, I've got 59 or 50 milliliters plus 49 milliliters, or 0.101, 0.99, oops, totally messed that up, 0.099 liters, because I've added 50 of this and 49 of this of solution. So the concentration of my excess will just be 0.001 divided by 0.099, which is equal to 0.001 molar. Okay, because I want to, that's the molarity of the solution. So therefore the pH is going to be negative log 0.001, which is 3. All right, so I'm at about a pH of 3. I still have a little bit of excess HCl. That's why. My pH is not neutral yet. When I get to the end of this titration, my pH will be neutral. It's not yet. I've got a little bit of excess of the HCl, so my pH is 3. All right, now what happens at the equivalence point? The equivalence point is when I have equal amounts of each. So I've got 50 milliliters of sodium hydroxide, and I add that to 50 milliliters of a 0.1 molar solution of HCl. The moles are equal to each other. The pH now will be equal to 7, and everything else, like my sodium and everything, are spectator ions. I don't have to worry about that. The overall net equation of the chemistry that's happening here is that, and we talked about that when we looked at our acid-base chemistry. Now, what about when we go to the other side? I've gotten to where they're equal. Now I'm going to add extra. So I'm going to add extra sodium hydroxide. So the calculations are basically the same. I've got the same number of moles of HCl in the flask that I had before, but now I'm adding 0.0051 moles of this. So again, now I've got excess, don't I? I have excess by 0.001 mole of hydroxide, and I've got this, my volume is now 0.101 liters. So the hydroxide concentration is going to be 0.00099 molar, and that's a pH of 11. Now, pOH is equal to 3, but then I use 14, and that gives you my pH. Now, what I would recommend you do is go back over. I did these calculations the same way as I did these. I have the excess. I take my excess number of moles, divide it by this 0.0001, divided by 0.101 is 0.00099. I can take the negative log of that, and it's basically 3, and so my pH is 11. Now, what's important about this is I've got 3 areas that I have generated in my curve. So if I took a pH probe and followed the pH through all this, I basically would have 3 areas. So this is the one that we just did. Basically, I started with a certain amount of HCl in my flask, so my pH is very low. And I start increasing the amount of sodium hydroxide that I add. So I go along the way, and I get to about here, and all of a sudden, the pH starts to go very rapidly. This right here is what's called my equivalence point. So I'm at 49 milliliters of sodium hydroxide here, and 51 milliliters of sodium hydroxide here. And at the equivalence point, I'm at 50 milliliters. So I titrate, it's very steady, it stays the same. Boom, I start to go through here. I go right through neutrality very quickly, and then I level off at a pH of 11. About 11 is up here. If I were to titrate in the opposite way, which means that I had a base and I titrate it with an acid, I would see the same thing, only I'm adding acid, so my pH is going down. It drops rapidly through the equivalence point, and then levels out at the bottom. So what we're going to do now is knowing all of this, in the next video, I'm going to summarize what we just did and what that means as far as the titration of strong acids and strong bases.